So again, welcome back to the industry readiness workshop. So for the case study demonstration that we have, we will be demonstrating a multi-phase simulation on ship resistance. We also have one more case, as Dr. Joseph Prabhu was saying, that he has submitted one research migration. So at the end of this session, I'll show you that case as well. If time permits, we will go through the whole case. So let's begin first with this case. So first you can head on to the website. You can go to case study project. You can go down to completed case study and you can scroll down to case study number 131. Okay. So this one. So multi-phase simulation using OpenFOAM to calculate ship hull resistance. Okay. It's done by Mr. Rishabh Sharma. So you can download this case study. We will go through this whole case study right now. Okay. So you can download. Yeah. So once you download it and extract the whole thing, you will have this one abstract and you will have the case files itself. So within that, you have multiple case files. Now over here, in this particular case, they are finding out the coefficient of drag or the drag force that is applied on the ship hull itself. Along with that, they have also compared four different schemes in multi-phase. So you have the Eulerian scheme. Since they're using volume of fluid, there are these four schemes that they're comparing. So you have Eulerian scheme, then you have Crank-Nicholson, local Eulerian interface, and the MPLIC one. Okay. So let's see what are the difference between these and what are the advantages and disadvantages of using these. So again, we are using this case study. So before beginning, for people who are not well aware of basically the parts of a ship, the hull is the lowest most part of the ship, the one which is in continuous contact with the water itself, and the one that faces the most amount of forces. Okay. So every time a ship passes through the water, this is the first place where you will get the most amount of force. So this has to be the strongest. So we are calculating the force acting on this particular area. Okay. For this, we have in the case study a simplified version of the hull. We don't have anything on top because we only want to find out what exactly is happening at the hull area. Now, in case you want to import your custom STL file and generate a simulation for the whole ship you have, you can do that as well. So for our case, we have a simplified version. This whole geometry and mesh is created in Snappy Hex Mesh. So we'll look at that as well. Yesterday we had a session on Snappy Hex, so we'll just go through that file. We'll see what changes are there and where exactly you can implement if you want to add your own custom files into it. And the end results, we are expecting the force, obviously, and we will also see the velocity and all the different contours that we have. We will also see various ways to post process your data because you have multiple ways to do that. You can do it using Paraview. You can do it using a custom Python code as well. In the case study itself, you have a custom Python code implemented. And at the end, I'll also show you another way in which you can write your own code and you can find out any data that you want using that custom Python code. And the solver used is interfoam. And we will also be using the volume of fluid methods within this interfoam solver. Okay. So first, the governing equations that we have, obviously we're solving for air and water, both of these. So for air and for basically both of the flows, you will have the Navier-Stokes equation. So you have continuity equation and momentum equation. Along with that, we will also be solving for the interface. Now, most of this Nikhil had already explained in the multi-phase uh, sessions that we had. We had two sessions before that, so he's explained in detail everything about this. So over here, just to give a brief summary of whatever was taught in the previous sessions, you have this particular equation that is for your interface, and then we have alpha, that is your volume fraction. So over here, zero, we have basically alpha fraction. Your volume fraction will depend based on where exactly, or your cells, how is it filled. So if your cell is filled with say fluid 1, it will behave as 1, like your volume fraction will be 1. Whereas if it is for air, then it will be 0, and if it is at the interface, it will be somewhere between these. Now in your interface equation, in your interface solution, you will have your density changing. So that density will be based on where your volume fraction is, whether you're solving for say air, or you're solving for the fluid itself. Okay, so your density will change based. So for that, you have this particular equation. And now coming to the schemes. So as I showed you, we have 4 different files. In each of them, they've used 4 different schemes. So you have the very first one, that is your Eulerian scheme. Then you have Crank-Nicholson. Then you have the local Euler interface. And then you have the local Euler MPLIC. Okay, so let's look at each one of them in depth. So the very first one is your Eulerian scheme. So this is the equation for the Eulerian scheme. It's a first order accurate in time scheme. Okay, it is typically used in solvers, that in transient solvers, that in which you require just a quick simulation, and you don't really have to bother that much about accuracy. So I would say that it is robust and stable, but it is less accurate when it comes to tracking the interface. Okay, so you will have some interface smearing, that is because of your equation diffusion. That is, you'll have your numerical diffusion in this equation itself, as it is a first order scheme. So you will have some smearing at the interface. So in case you want to refine that interface, you could go with the second scheme, that is Crank-Nicholson. Now this is a second order accurate in time scheme. Okay, so this one will resolve your interface. It uses, so obviously you will have less smearing and your diffusion is also less, but it comes at a cost. Okay, so your computation time will increase, which in turn will which in time will increase your computational expense. So if you have a powerful system and you have time to spare, you can use this scheme, and if you want an accurate solution as well. Now you know the very first one, that is your Eulerian scheme, and you know this particular scheme, the Crank-Nicholson scheme. So that brings us to the third one, that is your local Euler interface. Now, what this scheme does is, it it's obviously a first order scheme, so it is in par with the with the Eulerian scheme itself, because the backbone is that. But what it does is that it adapts the you can say the interface. Like, you'll have each cell that has its own local time step based on the current number. So what this does is, it will give you a refined region closer to the interface, whereas it can keep your current number, or it can solve for places where the cell is completely filled with air or water more quickly. So you will have a faster simulation with the output of Crank-Nicholson. Okay, so you have, like, it's a combination of both of those. It also maintains your boundness between 0 and 1. That is, it will keep it between your fluid and water. That means it is resolving your interface at high current numbers as well. It has an improved interface resolution, obviously. And it is so the downside for this is, firstly, it is a first order equation, so you won't get that much of an advantage when you're comparing to any of the higher order schemes, but it is computationally less expensive when you compare it in terms of orders. And it is slightly more complex to implement, because you have all of this going on right now, so you have to implement everything properly. So the implementation part is a bit complex. That brings us to the very fourth one, to the fourth scheme, that is your local Euler MPLIC scheme. Now, MPLIC stands for Modified Piecewise Linear Interface Calculation. So in simple terms, it is similar to the previous one. So it is similar to local Euler interface, with the difference being that over here it uses a geometric VOF algorithm. So what I mean by that is, it now your reconstruction part. Okay, so where your interface is, it will reconstruct that interface using this MPLIC geometry VOF reconstruction algorithm that is placed within this scheme itself. So this will accurately capture even small details that you have. So you will have a very refined interface. So this is extremely good if you want accurate solution, and like, you want to do in-depth analysis of that interface part itself. So it is good for that. This also has the local time stepping thing. So exactly what is done in the previous one, the local Eulerian interface, it does the exact same thing in terms of that. But this one is extremely expensive, because you are solving for every detail. So it will be very expensive when it comes to your computational part. So you need to have a high-end system to run this, because even on my system to run this simple case, it took around half a day to just run one-fourth of the whole simulation. Okay, so you can expect it to run for at least 2 days on a typical 8-core system. So you can keep that in mind when you're running. So looking at all of these four schemes, let's see what are the advantages and disadvantages in certain parameters. So when it comes to accuracy, you would have the Eulerian, like over here, higher is better. So you would have the local Eulerian MPLIC obviously at the highest. Your local interface one will be a little bit lower compared to Crank Nicholson. Now, this is just based on some data that I already had. So comparing those, I felt this was the accuracy graph, but it can change depending case to case. Now, in this particular case, this was the result. For Eulerian, since it's a first order equation and everything, you have quite a lower accuracy. And in terms of stability, the Eulerian case is a bit stable. Your Crank Nicholson may fail if you do not set certain parameters correctly. And the interface, obviously, since that local Eulerian interface scheme is based on the Eulerian scheme, so stability wise, both of those schemes are stable enough. And in terms of interface tracking, the last two are obviously better because they have those advantages, as I said in the previous slides, of that local time stepping and the interface tracking more accurately. So those two are much better as compared to Eulerian and Crank Nicholson. Now, in terms of simplicity, over here, lower is better. So you will have the Eulerian, it's more simple to set up and just run those cases. Then you have Crank Nicholson. Your local Eulerian interface is a bit simple to set when compared to the MPLIC. And moving forward in terms of time, so how quicker your simulations are running, obviously the Eulerian ones will run faster because it's a first order scheme, and you are not resolving many things in that. Crank Nicholson again increases a bit, and as you move forward in those schemes, the time keeps increasing. As I said, the last one, the MPLIC one, that one is resolving for most of the things that you require, so it will take the most amount of time. And in terms of computational cost, again, as your time increases, your cost will also increase. So these are the results for each of those cases. Okay. And this one is just an overview. We've taken four of the major parameters, that is accuracy, stability, interface tracking, and cost. So as you see, the Eulerian one is on the lower spectrum compared to the MPLIC one. So in terms of cost and everything, it is lower, but in terms of stability, it is high when it comes to the Eulerian one. And the MPLIC is obviously in par with the Eulerian in terms of stability, but it is also having a higher accuracy, higher interface tracking, but the cost is also quite high. So since we are done with looking at the whole statistic analysis, let's go to the case itself. So as I said, once you download it, you have these particular files. So the very first thing you do is always read the README file. So let's open that first. So in the README file, it says that Crank Nicholson, Euler, and local Euler interface, for that they have used OpenFOAM 2112. So in our case, we're just going to run it on 2412 because majority of the people will have 2412. And the local Euler MPLIC is made for OpenFOAM version 9. So that's why we've told you that in certain cases, you may require both of these cases. Sometimes you may require one over the other. So we'll run both of these in their dedicated versions that they have specified over here. The only thing is we'll run this for 2412. And then it also mentions you have some files. You have all solve that does everything. Then you have all run that only solves the whole simulation part with the mesh itself. And then you have all mesh that will create your mesh. And to clean the case, you can use foam clean tutorials. This particular command changes for OpenFOAM 9, it becomes foam clean case. So let's look at that. So you can minimize this. So first, let's go with the Eulerian one. So for Eulerian, you have again zero constant system. So you can open zero. So over here, we are using a turbulence model. So what turbulence model you're using, how you've calculated each of these values. For that, you can open the report. So in the report, you have all the governing equations. how they've computed the Reynolds number, then your turbulence length, how have they computed that, and also the turbulence kinetic energy. Those equations are also set over. So you can cross verify if you want to change any of these parameters. You can put in your values for which Reynolds number you want to run, what velocity you're running at. So all of those values you can put and you can change those values accordingly. Now, okay. So once you open the zero folder, you have alpha dot water. So last time Nikhil had explained this. So let's open this one. Okay. So at the inlet, you have a fixed value, outlet, and atmosphere. So all of these. So here we have our HTL file that we've labeled it as boat. So we have set that to zero gradient. And let's open the other one. So you have K, omega, P, R, G, H. So let's open K. Okay. So K, as I said, they have computed a value based on that formula that they have mentioned in the report. So you can cross verify whether this value matches with the ones that they have specified over there. And over here, they've again given some boundary conditions. So you can look into detail about these. We have those documentations already on the site. So you have the OpenFOAM site. So each of these boundary conditions, what they do exactly are mentioned perfectly in that document. So you can have a look at it. And at the that's like at your HTL file, you have a custom, not custom, but a particular boundary condition that is specific for this turbulence model. So you have the arc wall function, and that particular wall function will be based on this number. And similarly, then you have omega, P, R, G, H, U, etc. So we've already gone through all of these cases in the previous tutorials, in the previous sessions also. So we'll not go too much into detail about this. Then let's go to the constant. So again, over here, since we are solving for snappy hex, as yesterday Pari said that for snappy, you would have to create a tri-surface. Within tri-surface, you add the HTL file that you have. Now, typically, you would just have the HTL file. All these additional files wouldn't be there. Once you run snappy hex mesh, these extra files will be created. Now, bad faces is just, I don't think it's supposed to be here. By mistake, you must have left it there. But typically, you would have just an HTL file and the .emesh file. Now, and this particular file will be created once you run snappy hex. It just holds your extended mesh. Basically, when you do features mesh, all of these additional files are created. Then we have the gravitational values over here. This, yeah. So over here is where you specify your gravitational force. So it is in the negative. He's put in the negative z direction. So depending on the orientation of the whole block, you can see that. So let's first, I'll show you the block. So let's open this in the terminal. So let's type WSL. Then you type OF2412. Now, first we will just do block mesh to show you the mesh exactly and in which orientation it is set. So we have Panafoam. So this is your block, and as I said, it is oriented in the YZ coordinate system. Okay, the YZ plane. So it is that's why the gravitational field is put in the Z direction. Yeah. Okay, so now this is only the block mesh, so it's just your domain. We've not done anything to it. It's just a simple block. We haven't segregated it into air, water. We don't have the HTL file within it. So if I switch this off, like if I switch, okay. So if let's go to volume. Okay, 1 minute. Let's do paraform again. Okay. Let's keep it sunny. So if I switch to volume, okay, the volume is loading. But if you see within this block, we don't really have anything. It's just your domain. Okay. So first, let's close that. So based on that orientation, we have set the gravitational force and then we can go to transport properties and turbulent properties. So let's open transport properties. So here is where you specify your water, air phases, basically your phases, and you specify the properties for each of them. And surface tension we've kept to 0. So these are the parameters for your fluids that you will specify over here. You have your kinematic viscosity, then dynamic viscosity, all of those parameters you can place it over here. And lastly, then we have turbulence properties. Okay. Now turbulence properties is where over here you will change. If you want to run the simulation as a laminar case, all you have to do is change this RAS to laminar, and it will just bypass the whole block that you have set over here for RAS. It will take the simulation as laminar, and all of these files that you have put in your 0 folder, it will just ignore that and it will go ahead. It will only solve for your alpha dot water, U, and P, basically your pressure and velocity. It will not take any of these parameters. Now, in this particular case, they have used the RAS model, and within that, they've used the K omega SHT model. That's why you have the K, you'll have omega, and you'll have the nu tilde. That is your nut. So for the timing, let's leave this at RAS and save. Then once you're done with all of these, you can go to the system. Again, you have your typical, you'll have snappy hex, mesh quality, surface features. So let's open, so block mesh, it's a simple block. Let's open surface features. So again, as Paris yesterday mentioned, here you will specify your STL file. And then once you do your surface features extract command, it will run this particular whole file, and it will check your boat STL file. Then it will check the angle that you mentioned. So how much the curves, how much you want to capture the feature edges on those curves, how much you want to capture, that will be defined by this number. So if I were to specify over here, as they've mentioned, if you specify 0, it will not capture any edges. So you'll just have a simple block. And if you set it to 180, it'll capture all the edges. So if you have a spear, something like that, any curved surfaces, it will capture it much better if the number is higher. And then you have some base parameters, the subset features, anything you want to switch on or off, you can do that over here. You can just check from yes to no if you don't require that. Then once you're done with surface features, let's run this command. So first we've already run block mesh. We'll just run surface features. So now yesterday, Paris had shown you in 2412. Okay. So there are a few differences between this particular command, surface feature, and type tab, extract. Now in 2412, the command is surface feature extract. Whereas if you're running for OpenFOAM 9, it would be surface features. Okay. So this would be your command for OpenFOAM 9. So when we are running this case for OpenFOAM 9, you can notice this particular change in this command. Okay. So for now, we've done surface features. What this does is it will generate an e-mesh. Okay. It will first of all create all of these extended features and all. And along, okay, not polymesh, but in tri-surface, along with the STL file, it would have created this .emesh file. Now this .emesh file is important because in SnappyHex, as if you remember, yesterday Paris had mentioned something in which you can automatically detect the file, and in which sometimes you have to specify a file for SnappyHex to understand and to find out which curves are where. Okay, so let's open SnappyHex. So if you are using this particular feature in SnappyHex, so if you scroll down, okay, they've commented out most of the part. So there is one particular feature in SnappyHex that allows you to automatically detect the STL, or you want to use the .emesh file. So if you're using that .emesh file, you have to have that. So for that, you're using the surface features. Otherwise, SnappyHex will automatically detect the geometry and it will start to snap based on that automation that it already has. So in this case, we are not really specifying that, but ideally you would specify. Okay, so in the features part, they have commented it out. So over here you would have boat, and then over here you can detect that image file. So it will read that image file, all the data that it has captured within that image file, and then it will create your mesh accordingly. So let's keep that aside for now. Let's see the Snappy Hex itself. So at the start, we are using castellated snap, and but we're not adding layers. So for that, you have changed it to false. Then coming to the geometry, you have obviously a boat HTML file. So over here, you specify the file that you have and the name. And over here, they've also given the type that they want. So they've kept it as a wall. So it'll just behave as a simple wall. And then you have a refinement box. So you have refinement box 1 and refinement box 2. So they specified the coordinate system. How do you specify this coordinate system? In the previous sessions, they have explained this. So we'll not go too much into details. It's basic that you specify the lower limit and the higher limit of your box. Same goes for box 2. Once we do the meshing, I'll show you the refinement regions as well. Then you have your castellated mesh control. In this, you will specify how much cells you want. So your max local cells, max global cells, how much refinement cells you require. Over here, they have minimum refinement cells. So here they've set it to 0, and the cells between levels. So if you are changing from a level 1 to level 3, how many cells in between of those you will require. So it is not a drastic change. So that you can specify over here. Then features, again, over here, you'll specify your image file. In our case, we are not doing that. Then we have the resolve feature angle. Here they've set it to 45. You can again lower or increase this number. You can see then what happens when you do that. How much faces and how much curves it is capturing. And over here, then you specify distance and all region-wise refinement. They've just switched all of that off. So refinement region over here, they've specified the levels. It's 1 and here it's 2. So you can change that. Again, location in mesh. Yesterday, Paris had very nicely explained this, that your this location in mesh point has to be exactly inside a cell within your domain. It does not have to intersect with any of the lines or any of the points that are there within your whole domain. Otherwise, it may throw an error. So you can check that as well. He had also explained how to find that particular point using that one filter in ParaView. So you can check that as well. Allow freestanding, yes, we've kept that. Snap controls, again, they've changed this. Now over your tolerance, how much tolerance you have for that snapping feature. So here they've set it to 1. If you have a good enough case, then you can set it to 1. If you have a medium mesh in which you're not really sure whether it is good enough or not, you can set this value to 2. And if you have a really coarse mesh, you can change it anything above 2 is fine. And your solver iterations, how many iterations it will take to snap. So those iterations are set to 300 relaxation. Now add layers, since we're not really doing anything, we've set it to false. So it will not create or it will not add any layers over here. So that is set to false. So any of these features will not be added to the whole geometry mesh itself. Feature angle, all of these features are there. And then at the bottom, we have mesh control or your mesh quality. This will basically just check whether your skewness is within this range, internal skewness, all of these things Paris has already explained last time. So we'll not go too much into detail about this. So let's close this. And then we have the set fields dict. So in this, you are basically setting which particular parts are your air and which one is water. So all of those things are set within this. So you have box to cell, box to face. So anything that is within this cell, you are specifying it as water. So you've specified alpha water 1. So 1 means that it is filled with a particular fluid. Now in our case, we have set it to water. So anything within this particular box will be water. And anything outside this box, we have default field value set to alpha dot water 0, that is air. So in this way, you can specify which parts you want as water, which parts you want as air. If you have multiple fluids, like if we had water, oil, and air, so you can change all of these. You can specify certain zones or certain areas in your whole domain as whatever that fluid is. Now, Nikhil had already shown that as well. He had done a dam break case in which we had 4 different fluids. So you can check that. It was day before yesterday. You can check those recordings as well. So once you're done with set fields, you have refine mesh. We'll not go too much into that because there is a particular um, thing while running these cases. So you have to switch off some of these parameters for it to properly run. Because in the past, there were a few people who were complaining about the case not running. So I'll try to resolve that as well. And then we have our basic block mesh, control decompose, FE schemes, FE solution. So first we'll go to the FE schemes since we are changing schemes over here. So you see the schemes that we're using over here. The default one is Euler, and you have set some parameters for that accordingly. Now in the different files that we have, so you will have Euler, Crank-Nicholson, local Euler, depending on which one you're using, MPLS, your interface. So all of those will be changed over here. Okay, so your FE schemes. So you're trying to compare the interface tracking for all these 4 schemes as well. And lastly, we have a decompose. Now this particular decompose is set to 80 subdomains. Now on a typical system, you won't have 80. So we'll change this to say we'll change it to 4. Okay, because my system has 6 cores. So again, we've shown this in previous sessions also. We'll just have a quick look at that, how to find out how much cores you have on your particular system. So you can do that using the LS CPU. Okay. Now you can do 2 things. Is you can either run each of these commands manually. So we know that we're using snappy hex. So we can first do block mesh, then you do surface features, then you can do snappy hex overwrite. And after that, then you can run your solver itself. If you want, you can decompose it as well. You can use decompose par. So you can do all of these manually, or you have the all run case. Okay. Now in that previous README file, if you remember, they had specified that you will have an all solve, all run, and all mesh. Here we have also an all plot file. So in the all solve, as they said, that you will have it to do everything. So all solve is just running all mesh and all run. Okay. So let's look at all mesh first. So now if you're planning to run anything using the script, always check how much files or not files, how many domains they have set this to, because now obviously 80 would throw an error. So let's change this to 4 and let's change this to 4 as well. Okay. Now the redistribution part, you can comment it out because we're not really going to do that much with the redistribution part. And in the other solvers, it may give you an error as well. So let's keep this as commented. So we're just running. So say if we have alpha.water, like if you've run this case, it will create an alpha.water. That's why we've labeled it as alpha.water.org, because Nikhil must have already told you this, that when you're running any multi-phase case, if you have water or any of these files, it will overwrite this file with the data that it is currently calculating. So it's always beneficial to keep this alpha.water as an original file. So if you want to make any changes, you will have that original file. Otherwise, you will have just an overwritten file. So what we're doing is we are deleting, if in case there is an alpha.water file, we are deleting that. So this is what this command is doing, rm. Then cp is just copying the original file to alpha.water. Okay. After this, now for the meshing part, these 2 commands are not that important, but when you're running a simulation, these 2 will be extremely important. And then we are just doing a foam clean case. Again, if in case we have any old files, it will just clean those. It will make a 0 directory. Now, this particular 0 directory is for snappy hex, because snappy will create its own cells and all of those things, and it loads everything within that 0. So what we'll do is we'll try to run it manually for now for the meshing. So the very first thing we'll do is we will change this 0 to 0.org. Means we'll keep our original 0 file separately. We don't want anything overwriting it. You never know that if something will overwrite it or not. So let's keep 0.org. So within this, we have all of our original files, and we'll make a copy of this and we'll place it here. Okay, so we have a copy. We'll label this as 0. So if any changes happens also, we at least have the original file. Okay, it's a good habit to always do this, because if you have any files that are overwritten, you have some files to look back at. So let's delete this. Okay. So we have now our 0 file, the copied one. And now we'll just do our meshing. So like if you're doing snappy hex, you will first do block mesh. So first let's clean the case. Home clean tutorials. Okay. So first let's do block mesh. Then we do surface features, extract. Okay. Now once we've extracted all the edges and everything, we can do snappy hex mesh dot dash override. Okay. So your override command is in simple terms just overwriting any previous data that it has, and it tries to interpolate the points that you have with your STL file and the block mesh itself. So it's just trying to merge your block mesh and your STL file together to create one uniform and unified mesh. So your snappy hex will take a little bit of time. Max it takes like around 1 minute. So let's wait for some time while this meshing is done. Okay, so now it is doing the snapping iteration. So you see we set the iteration to 300. So after 300, then it completes that. Okay. So it will be done now. Yeah. So once it is done, we'll just see the mesh itself. So you see previously we just had the block, the domain. But now if you see on the left-hand side, we have this patch boat as well. So I'll switch off the internal field. We'll only keep the boat. So this is our mesh for the ship itself. Okay, let's keep that surface. So I'll switch on the internal patch and we'll take a slice to show the mesh. Okay, let's take this one, apply, and we'll switch on surface with it. Okay, so you see we had specified the refinement box. So we've had a refinement box over here and the second one closer to the geometry itself. Okay, so we can switch on the show plane and triangulate. Okay, we have here. Okay, so this is your mesh. So we will have the interface also somewhere around here only. That's why we've refined the whole region around this place to have a much more refined interface tracking. So this is about the mesh. So now let's run the simulation. Okay. So for this, we have the all run. Okay. Let's open this. Now your all run, as I said, if you have any alpha.water previously, it will just delete that. And then we will copy the original file. Now we ran our case for Snappy Hex on a single core. So we don't have any of those processor files. If you are running it in parallel, like if you were to run the all mesh file, the all mesh would have decomposed your domain. Yeah, over here it would have decomposed. So let's keep this open. It would have decomposed your domain and then ran it in parallel. This is what the command would have done, and then it will reconstruct the mesh. Okay, so it will run a bit faster. For the second case, we will run it in parallel. So I'll show you that as well. So okay, all right. So what this is doing is it is just going to clear all of those processing folders because we want to run this case in parallel. Then if we have any post-processing file or something like that created, it will delete that as well. Now, the second thing we will do is set fields because we have to differentiate between air and water. So set fields will run that. And then we will again redistribute your whole thing. For that, we can or you can either do decompose like that, or you can just uncomment this part and comment this one. So we'll keep this, because when you're running any of the Crank Nicholson or any of those particular cases, now in Eulerian, these particular commands run fine. But in your Crank Nicholson, the local cases, it gives an error. Okay. It won't give an error, but it just gets stuck at finalizing parallel and all that thing. So for those kind of, to avoid that error, we are just doing a simple decompose, and we don't really need the renumber mesh. These particular commands are just so that your solver runs a bit more efficiently. If you just decompose it and then run it in parallel, sometimes it, obviously these cases will take time because they are a multi-phase case and you are running multiple things at one time. But there are multiple ways in which you can speed up that process. Like you have hyperthreading and all of those. Like if you open one of these files, there is a particular command for that as well. So we can, for now, we'll just comment this out. We'll just do a simple decompose, and we will just do simple parallel running and a simple reconstruction. So we'll keep this and we'll comment out these. Okay. Again, we'll change this to 4 because we only have 4 cores. Yeah. And speaking about cores, if you want to find out how many cores you have, you can again do ls CPU, and you can scroll on top to cores per socket, that is 6, and sockets you have 1. So you have just 1 socket. So in total, we have 6 cores. So I can use a max of 6 subdomains. Yep. So we change this to 4. So now we'll use this particular file only to run the case. Yeah. And one more thing. Now, when we are running the MPI run, if you notice that in previous cases, when we were running it in parallel, we were just doing up to here. MPI run NP, that you're specifying number of processors, 4, and then your solver name and parallel. But over here, we have added an extra line or an extra command, that is log. Okay. So if you just type this particular command and you run your simulation in your terminal, it will just run everything in the background. Okay. So it will just blink your cursor over here and it will show running parallel, and you may think that it is not running something, but in the backend it is running. So I'll show you how to see that backend also running. So let's run this particular command first. So the command said that we have to do set fields. Before that, we'll go to the 0.org. Okay. Okay. So see, for like these reasons, you should always have the original file. Now it's not allowing me to, okay, deleted that. Fine. So let's copy this particular file, copy paste, and we'll keep this as 0. Okay. Now you can delete all these zone identifiers, and let's change this 0. Before this, we'll just copy this, copy, and we'll change this to alpha.water. Yes. Okay. So now we have our alpha.water, and we have the original files as well in our 0 folder. So as per the sheet, we had to change that alpha.water. We don't have any processes, so we're not deleting any of those. We'll do set fields, decompose, and then we'll run it in parallel. So you can do set fields. Okay. It has differentiated your domain, so you can see that. So we have now, this is our domain, and now you can differentiate between patch atmosphere, patch bottom. Okay. Okay. Once you run the simulation, you'll be able to see it properly. Let's do that as well. So we'll do decompose. Now we've set to 4, so it will decompose it into 4 subdomains. And if you do mpi run dash np 4, number of processors 4, interFOAM, and then you run it in parallel. Okay. And as per that command, you want to log. Okay. So let's cross verify. Okay, the command is different over here. So we want to log this particular file. Okay. Okay. Parallel log. So if I run this, now you see it is just blinking my cursor over here. So sometimes for people who run this command the very first time, they might think that nothing is happening or my terminal is hanged or something like that. But if you see, now if I refresh it, you have processor as well, and you will have this log file. Okay. So it is logging everything that happens in the terminal into this particular file. Okay. Now this is good if you are planning to post process something or you want to check your residuals after you've run your simulation. So for those kind of cases, it is good to log your files so that you have this data and you can plot it later on. So this will keep refreshing every time. Now, in case you want to check it on the terminal itself, okay. So I can just open CS new part of the terminal, type WSL OF2412. Let's go to the path that we are running our case in. So we'll go to run. Let's do ls. So we're using the multi-phase ship case. So let's do cd multi-phase. Again, we'll do ls. We have cd multi-phase. Again, we'll tap ls. Ls will just list everything that is there within that particular folder. And now within this, we want to go to Euler. Okay. So ls over here is happening. Yeah. So you can clear this whole thing. Let's clear this. Like you want to tail or you want to find out exactly what is happening in this particular file continuously. So you can use tail dash f and then you can type your file name. Okay. So if I do this, it will start tailing that what is happening in that particular file. You can check it in real time. So you can check whether any of your solutions by looking at the, like you can read the terminal and you might know at that moment that your solution may diverge or it is converging properly or the results that you're getting are fine or not. Now in our case, it is giving you the forces. So you can check the total force, like you have the total forces, then you have pressure, viscosity, and all of those things. So you can check these parameters whether they are aligning with something you're trying to validate or it's at least close. So this helps in when you are not sure whether the parameters that you set are correct or not. Then at that moment, you can just switch off your simulation and you can then start a new one. Because sometimes it may happen that you have done your whole simulation and then you realize that you forgot to place that one particular parameter and now you have to again rerun the whole case, so that much time has got wasted. So for those kind of cases, it's always good to check all of your these parameters that you are trying to find whether they are accurate enough or not. Now this particular terminal, you can just press Ctrl C and terminate it, and it will not terminate your original case. So in the background, this is still running. So you have this benefit as well of using the log command and trailing it in the other secondary terminal that you have. Okay, so if you are running the simulation using this particular file, you will have it display something like this. Okay, so don't think that it is not working or something like that. It is running in the background. Just make a note that it is showing a log file and whether that log file is getting updated or not. So first it was 7 KBs, now it is 82. So it is writing some data inside it. Now, this particular case, we already have it run. So we'll stop this. Just press Ctrl C. So I'll show you the run results. So we have for Euler. Let's open this. Listen, F2412. So here we have, instead of pressure, we click alpha dot water. Okay. Just click on this one. I'll drop down the opacity and enable that boat patch. Okay, let's switch to 2D. Okay, so now this one has already simulated your multi-phase case. Now over here you have the fluid, here you have your air and the interface over here. So now we'll try to compare whether what advantages and disadvantages I said, like interface tracking for Euler is not that great and all. We'll try to compare that. Okay. So we'll keep this, we'll increase the opacity. Okay. We'll load all of these side by side and we'll see that. So for now, we only have the Euler case run. So if you want to post process the data, like how in the report it was, there are multiple ways. You can use a slice and you can define your plane Z. You can move it up or down, change to 3D. And let's say we want it at, instead of, want it a little bit at this range, apply. Okay. And instead of P, we want to see the velocity. Now this is for air, whereas if you want to see the velocity of the fluid itself, we'll lower this a bit. Line. Yeah. So if you run the simulation for a longer duration, you will see all of those contours that are there in the report. Now, in our case, we've just run it for a short time, so we are not able to see that much of it. So this way you can post process. You can use a slice or you can use clip. So there are multiple ways to do that. You can even load the boat separately. Like if I click on open, we have this small window. So I know that my HTL file is within the constant try surface. So I can load this boat HTL. So this way I can keep my boat. So we'll switch off from the main file, the boat, apply. Okay. So for this, you'll have to load it separately and keep the opacity of the whole domain also less. So this way you can load your HTML file. You can see how exactly the contours are there. So if you want to visualize any of these, you can do these particular ways. Now this was for Euler case. Okay. Let's close this terminal. Yeah. Now we'll run the same thing for Crank-Nicholson. Again, the procedure is the same. There's nothing different as such. You only have to make a few changes over here while running for these cases. So I'll show you the key differences that we have between Eulerian and all the other cases. So you'll have firstly the scheme change. So over here we are specifying the default Crank-Nicholson 0.7. So over here we've changed the scheme. Along with that, you have to change your decompose power, because in each of these cases it is set to 80. So we don't really have 80 cores, so we'll set everything to 4. And this time I will run the case in parallel for SnappyHex, so that way you will see those files generated. Now for all mesh, you'll open this, set this also to 40, this also to 40. We'll keep everything as default. And we'll change all run. We'll change. Now we don't really require this particular decompose. Okay, for now, I'll show you what exactly is the error that you get. So we'll leave this to 4, everything to 4. Okay. So for now, we've just left everything at default. We will close this terminal, close all. Okay. So now let's open in terminal. Okay. So first we will just do foam clean case tutorial. Okay. And we will first run bash all mesh. Okay. So all mesh will first run your surface features, then it will run your block mesh, then it is going to run your SnappyHex override. Before that, it will decompose everything. So it decomposed and now it is running in parallel. So while it is running in parallel, I can show you. If I see, so okay. So in parallel, we have decomposed the whole domain into 4 subdomains and we're running on each of those processes. So the meshing will be a little bit quicker as compared to last time. Last time it took a little bit over 2 minutes. This time it will be a bit quicker. So you see over here, it will create the mesh and then once it is done, it will reconstruct it. Now in a 0, we have created that alpha.water because in the script itself, it has set that it was set that way. So you have all mesh, it will create that alpha dot water and it will clear any old ones which were there. It created that zero dict also. It's on the snapping part. Now, when we are running the all run, it will first delete all of those processor files. If any post-processing file was, it will delete that as well. And then it will basically decompose the whole domain and I can run the whole thing for the simulation this time. Okay, so now it is done. So now let's run bash all run. Okay, so it first will clear all of those files. It will clear that and it will again make everything. It will decompose. It is running set fields now. And now it was running the decomposition part. Okay, so if we, yeah, so it decomposed the domain, but now it is stuck at this part only, finalizing parallel run, and it keeps getting stuck at this only. It does not do anything more. So to avoid any of these errors, you can just stop this. And over here, you can just do a simple decomposition. So you can comment this one out and you can enable this one. Same goes for renumbering. Okay. Okay, so once done, Paris, can you let me know?
Sure, sir.
Yeah.
We can start, sir.
Okay. So once we've made the changes, like you can comment out the redistribution part, renumber part, and you can keep the normal decompose and normal reconstruct. So once we do that, we'll just run all run because it already has the foam clean and everything inside it. So now it is decomposing. It decomposed the mesh and then it is running in the background. So again, we can check that using the WSL OF 2412 and we'll go to that particular file path. Yeah. So here we have, not Euler, sorry. This time we're running the Crank Nicholson, right? So we can do tail -f log. Okay. So you can see over here it is running in the background. You can cross check it with the log file that it creates. Okay. So in this way, you can make the changes, necessary changes to the other files as well to avoid any of those errors that pop up. Okay. So let's stop this one. Now this particular case also we have it already run. I'll just show you the next changes for interface because the MPLIC one is made for OpenFOAM 9. Okay, so yeah, for the interface one, again, changes are first you will check in your FE schemes. Over here, we have local Euler. And you can then make the changes in your decompose par. Now, in this case, it is set to 6. If you have 6 cores, then it's fine. So you can change this, and in the all run, you can in your all mesh you can change that particular parameter for decomposition and in the all run as well. Okay, now you also have this additional file named all plot. Let's talk about that a bit. So in all plot we are just plotting that force that we require. Okay, we're trying to find out the force acting on the hull itself, right? So we are using this Python code for doing that. So in this particular file, you have the Python code itself. So you have it, it is just a basic Python code. It's just reading the post process file of forces like over here. I'll show you the run case because we have that over there. Okay, I can't really go on top. Yeah. So we have, let's see the Euler case only. We have this run. So we have this post processing. Okay. So when you are running, you'll have post processing forces under zero, and you'll have multiple, you don't have multiple, but you'll have a few files. Okay. So you have this force file. So you can open the DAT file. Yes, good. Okay, so over here it is logging all of those things. Like when you're running it on your terminal, as you saw, it was showing you the total force, that was showing pressure, it was showing viscous. So all of these force in their XYZ coordinate system is saved over here. Now we just have to extract this particular data and present it, or at least put it into a formula for computing the force part in a graphical representation, right? So for this reason, you can do this using the Python code itself. Now that is provided over here. So you have this plot. So what that is doing is under post processing, under force, under zero. Now they have added that run sh. So under that run sh, it is just trying to find that. So that run sh is over here also. It's kept out there. So that run sh is again opening the post processing force zero force dat. Now over here they have complicated it a bit by adding multiple files into a file that are sourcing the exact same thing. So you can modify this, you can write your own custom code. So we still have half an hour, so I'll be able to show you that Python code as well. So for now, you can run this particular file. So let's do that. So let's open this in terminal. WSL OF2412. And if you want to plot anything, you can plot that Python code itself. You can just type Python 3, and then you can type the file name. The file name was plot.py. Okay. You can just type enter. Now over here, it has generated this file. Okay. So you can close it directly, or you can first terminate it from here and again press terminate, and then you can delete, close this file. Okay. So you, okay. So you just hit it multiple times, it will terminate that operation. Or you can also do dash all plot. Okay. So it does the exact same thing, but here it is just a bit automated. So you don't have to run multiple commands. Okay. So again, you just, yeah. So it terminates that. So you can just do Control C to terminate the whole operation. So this is one way to plot your data. Okay. Now I showed you for the first three, Euler, Crank-Nicholson, and local interface. So let's see the MPLIC one. Now that is made for OpenFOAM 9. Okay. I have the case over here though. Okay, this is for run case. So this is the run case that I have. I did not run it for the entire time step. Like it was ending at, you can open the control deck. So you see, it is ending. Now I've changed it to 500, but ideally it was set to 10,000. So obviously 10,000 will take a lot. Like to just run 500 iterations on 7 cores, it took about half a day. So you can expect this to be computationally very expensive. Now, if you have a high-end system or you have a cluster system, you can run this a bit quicker. And also for for the post-processing part, okay. Now, in this particular file, like if you see the run file, in post processing, now this particular file isn't just directly created like that. Okay, you need to add a particular function that during your simulation it will try to compute things based on that. So where do you specify this function? Like now we want to compute the force, so we need to specify a force function that will be computed when your simulation is running. So that force function is added in your control dict. If you scroll down after your runtime modifiable, you will have this additional tab known as functions. Within this, you can specify your force block. Now your force block over here, what it is doing is it is first of all computing your forces. So it is directing it towards that lib force file. So it is trying to find that library for forces. In that all the formulas are there, which patch you are using. So it is going to compute the force on the boat patch. Okay. Now, if you have like flow over a cylinder and you want to find out the drag of that cylinder and all, if you have like cylinders in tandem or you have multiple cylinders and you want to find out the drag for each of them, so for those kind of cases, you would have to differentiate out all those patches. You can't just label them under cylinder, because what this does is, like, now if I had a boat and behind this I had another boat in a tandem configuration, and I wanted to find out the drag of the second boat, so I would have to label the patches separately. Okay, so I would have to label it as boat 1 and boat 2. If I put both of them together, OpenFOAM, what it does is it will combine the area of both those patches together and it will give you the output. So that if you're computing for boat 1, it will give you the same results. If you're computing for boat 2, it will give you the same results. It will not differentiate. Whereas the drag for the second boat should be lesser compared to the first one. So if you're running multiple patches and you're doing some multiple simulations on different geometries, make sure you segregate those patches out separately. Okay, otherwise you might get the same results for all of them. And then rho infinity. Now here you're specifying your viscous and all of those parameters for water. So accordingly, they have changed it. You wanted to log the files during your simulation itself. It in your terminal or when you're running a simulation, it will log those files. Either ways, it is going to log it into that particular file. If you want to just check while the simulation is running, you can switch this on or off if you don't want to see it. Right control is your time step, and this is your coefficient of rotation and all that. So over here, you don't need, usually we set it to 0. Over here, they set it to 0.01. So you can check all of those things. Okay. Now, if you want to find this particular block, you can go to, let's open a new one. Let's go to Ubuntu. And now if you are, again, OpenFOAM 9 is in OPT. So let's go to OpenFOAM 9, OpenFOAM 9, and let's go to the applications, or again, you can check an application utility and post process. Okay, these are for creating those. If you want, you could do that file search. So you can open this particular thing in terminal and you can just do grep. Okay, first you have to go into WSL OF9 grep dash R, and then just let's type force. Okay, so now it has given me so many searches for just force. So then you can open one of these tutorials and you can copy paste that particular block that you want. So it is saying that, see, in mesh in control dict include force coefficients is there. So if I want to find anything with force or force coefficients, I can copy in these particular blocks. So let's go to tutorials mesh, snappy hex mesh. Okay. So in tutorials, under mesh, under snappy hex mesh, under motorbike. Okay, so wait, let's see the terminal again. Okay, so under motorbike system, snappy hex mesh, motorbike system control dict. Snappy hex mesh, motorbike is a file though. Let's check another one. The tutorials compressible RAS Naka. Yeah, this one is there, fine. Let's go to compressible. This one is for row simple foam. Row simple foam, Naka airfoil system, checking control dict. Okay, here we have one. So over here functions, they have used force functions and all of those. Now here they've just included as a function. So you can check the included files. So over here they mentioned force files. So over here they are checking the force coefficient. So you can again copy these particular blocks into the file that you require, like in our case over here. And then you can change the patches based on the patch name that you have or you're trying to compute it. So you can find out your force coefficient, forces, if you have some wall shear stress, all of those parameters are there. So you can post process all of that using a custom Python code. But if you're using a Python code, they have to be first enabled over here. So only then OpenFOAM will save a file with all of that data. Okay, so you can do that this way. So let's look at the file that we have to see. So the MPLIC. Now this one is set for OpenFOAM 9. Again, you can open the system. You can open, not control it, FV schemes. FV schemes, then here, see, we're using the local. But over here, if you scroll down, we have the Gauss, means which div scheme we're using. The schemes that we're using under that, we have changed it to MPLIC. Okay, so these changes are there in the FE schemes. Okay, so for now, let's just try to compare the results. Okay, let's see whether that interface tracking is good enough or not. So for each of these files, I'll first create a .foam file. It will make it a bit easier rather than opening them in multiple terminals. So this one is for OpenFOAM 9, and we'll just do touch results.foam. Okay, so let's close all of these. Okay, so over here we do, okay, so we do have a results.foam, and okay, yeah, so MPLIC done. For interface, we do have a .foam file. Okay. For Euler, we'll create one. WSL. Touch results.foam. Okay, and let's go to Crank Nicholson. Again, we'll do touch results.foam. Okay. Yeah. So we've created these .foam files for each of them. So we'll just open Paravi for one of these. Let's open for Euler. Two for 1, 2. And then we will just do Parafoam. Okay. Click on apply. Okay. So we have this particular case. So this is for Euler. Let's open one. Okay. Before that, we'll split this into render view. And for this particular file, we'll open Control O. And instead of Euler, we'll go to Crank Nicholson. And we'll open the .foam file. Apply. Yeah, we have this one. Instead of pressure, we'll change this to alpha.water. Go to the last. This one we will also orient it this way. Alpha.water. Last. And let's split each of these. Okay. You can. Okay, you can't really drag it over here. Okay, here this one. So for this particular one, we will set it to the local Euler interface one. So for the interface one, we'll save this one. Okay, let's orient this one, and we'll change this also to alpha.water. And over here, we will change this to the MPLIC case. apply. Yeah. So we'll change this to alpha.water. Let's go to the last one. Okay. Now this one hasn't converged completely and the simulation wasn't completed. So it's giving some disturbance. We'll take a slice for each of these because the mesh is a bit refined when it comes to X normal. Yeah. We'll change this to alpha.water. This one was for this. Okay, so let's change input the slice to interface one. Okay, so this slice is for interface. This one we'll add a slice. Okay, so this one is a bit distorted. And this is for the second case that we have. Add a slice for that. Okay, switch to this one. Slice, apply, change to alpha.water. Okay, and finally this case, we'll take a slice for this particular case. Okay, let's zoom in. So this is for Euler. Let's show plane. This one also show plane. For this one also close the show plane for all. Mhm. Okay. Yeah. So you can see the diffusion, the numerical diffusion that we have. This one, do not take a slice. Okay. Just delete the slice. For this one, we'll take a slice. Yeah. Alpha dot water into this one. Yeah. Mhm. Okay, my bad. Okay. Understood. Hmm. And then we have this one. It's a bit distorted, so we can't really see that much. So the Eulerian one, if you compare just the Eulerian and the Crank-Nicholson, so you see the difference between the order. Like as I said, the very first one is first order, this one is second order, and this one is also it's based on the Eulerian, both of these, but it's just that we are changing some of the, like it has the local time step capability. So this one is a bit smeared compared to the Crank Nicholson. The Crank Nicholson is much more refined. Now, this one, if we were to run the whole case, this one in theory should be much more clearer than compared to all of these. But again, due to the time limitation of the whole thing, we can't really run that case. But fine. So this is just a basic comparison that they've done. Like if you check the report also, here they've compared the residuals for interface, that is your local case, local Euler, and the MPLIC one and the Crank-Nicholson one. So you can have a read of this file as well. And over here, they have done a result comparison, forces plot. So how does the force change, or at least when you're running these cases, how does it affect based on these particular uh, schemes. So for Euler scheme, you can see the case, and for Crank-Nicholson is in blue and the expected results. So based on these schemes, which one is good over another and for what types of cases you need to run those, you can see that. Now, as I said that Dr. Prabhu had also submitted one research migration. So you can check that research migration under research migration tab. You scroll down to completed research migrations and you can scroll down to, okay, see here. So at case study 26. So this particular case of his is also there. You can read this, you can download it. This is also on hull resistance only. So you can check this out. How is it different from the one that I demonstrated, and which schemes he's using, and why those schemes are better off than the current scheme that we are using in all of these multi-phase simulations. So you can do your own comparison. So if you are into, say, the shipping industry and you want to find out which particular ship hull design and how much resistance it is causing, so for those kind of simulations, you can do your own study, and based on that, you can again compare schemes. You can compare different methods that you have, different geometries as well. So that can be done in OpenFOAM as well. And coming to the Python code, now the one that you saw was a bit simple. So you have a very basic. You're just copy pasting the whole thing, and you're just finding out your coefficient of drag, your not coefficient, but the drag force and all those other parameters. But in case you wanted to find out, say, straw hole number or your at least coefficient of drag or coefficient of lift, so you can write a custom code like this as well. Like over here, you can see that we have mentioned the length and the your characteristic length and your velocity, because in straw hole calculation those are important. But if you just want to find out coefficient of drag, coefficient of lift, you can add those formulas as well. It's a simple formula, so you can add those. You can see the fluctuations, and then once you plot it, it will give you a nice graphical representation of your data. So if you want to find out CDCL, like for an airfoil case, you need to find that out. So you can run your own custom Python code. So see, the limitation in post processing is not restricted to only coding in Python. Like most of the people might not know Python, so for them, paraview is there. You can use the calculator feature. So in ParaView itself, on the left hand side, if you click any of these, you have this calculator feature on the top left. So over here, you can select a particular data. You can select a particular data set, and you can add your own custom formula for it, and it will plot your whole graph for that. And then you can export that particular result as, I think Manzil had shown here, that you can remove the CSV data for that. So you can plot that out as well. So there's no limitation when it comes to post processing or how to visualize your result. When ParaView is overall capable for doing that. You can see all of those things. Okay. So yeah, that brings an end to this whole case and the simulation and the demonstration part. So if there are any questions, we can take those questions now.
Sir, there was a question
Mhm.
regarding when to use the zero gradient parameter.
Zero gradient parameter, right?
Hmm.
Okay.
In the
So
boundary.
in terms of velocity, if you are using zero gradient, you would typically use it for far field conditions. So basically, zero gradient, what it does is it just takes the very last cell that you have and it just applies that to that boundary condition. So whatever is happening in that very last cell of yours, it will apply that as the boundary condition. So you can say it is adapting based on how your simulation is going ahead. Whereas the fixed, any of those fixed values that you have, those are like hard coded, or you're fixed those values, so your cell cannot do anything else besides running that particular boundary condition that you applied. So that is when you will use zero gradient, when you are just trying to simulate some far field condition, or you just want to, like, that's why we use it at, usually at simple cases we use it at the outlet. In far field condition we use it at top and bottom if you want an open channel or an open simulation. It's not constricted by walls or anything. So for those types of simulations, you can use zero gradient.
So there is a question in the chat box.
Yeah. Okay. So the all my section topo set present any requirement. Okay. So 1 minute. I'll just check that. I may have missed that out in all mesh section. Could you specify plugin in which particular case? It will help me find that out faster. Euler case, no? Okay, wait. All mesh. So I was saying in this particular case, you have a few commands that are commented out, like toposet, refine mesh, all of those. Now for toposet, I'm not sure. Wait 1 minute. Is the file there? Yeah, toposet is not there in the system file. So your toposet is just you are defining a set of cells to behave in a particular way, like you are segregating that out. So you can give conditions like if you are running a CHT case, that is when your toposet and all those files will come into play because you have your domain, and within that particular domain you are specifying a set of cells to behave like a solid or another material. But in our case, we only have the HTL file and we have already segregated out air and water using set fields. So toposet is not really required. Now this case is a bit old, so you might find some older, like whenever we are submitting the newer cases, if you see, we try to tell the interns not to type or leave any of the previous commands that they are not using, because it creates a bit of a confusion to a person who's just trying to run a case. So now like how you said that will you be requiring toposet or not, now in this case you don't need toposet, so you can just bypass all of that. Okay, hope that answers the question. Okay, so when running, it is running fine, but when coupling with different governing equations, it's not clear. So what exactly in the governing equation it is not cleared? Because see, your schemes, like if you're just trying to run something by changing a scheme or sometimes, so in that FV schemes, you have multiple parameters. So you have to check your DDT schemes, you have to check your div schemes. So all of those have to match. Again, those everything in that particular file is mentioned on the OpenFOAM documentation that you have. So which particular schemes are present in your OpenFOAM 2412 and OpenFOAM 9. So those things are already mentioned, which ones you can use. So how exactly should we couple the RANS equation with the other governing equations in the model? Okay. So RANS and all of those, like if you're trying to implement turbulence modeling in your constant, you have the turbulence properties. Okay. Okay. So now when you type RAS, it's not that you are coupling anything separately. It is already pre-built and fed into OpenFOAM. So when you just type this keyword, it knows that RAS is your Reynolds average Navier-Stokes equation, thing. So you have to run that whole thing. So it OpenFOAM knows which particular model. So over here you can run RAS, you can run laminar, you can run LES also. So again, when you type RAS in this block, you have to specify which particular RAS model. Now in RAS itself, you have K omega, you have K epsilon, you have various different, you have K omega SHT as well. So all of those schemes, you have to mention which particular model it wants to solve. Because if you open the back end, like I can show you, let's, okay. So let's go to the back end. If you want to see in tutorials, OpenFOAM 9, let's see. I don't exactly remember whether it was in applications. Let's see, utilities and the post processing. No. For turbulence modeling, there is one particular place where they store all that data and you can open that. I think it was in SRC. Under SRC only it was. Let's check. This is OpenFOAM's original files. So you can check under OpenFOAM, like under the OpenFOAM thing, instead of tutorials, there are multiple files. Within one of those, it specifies exactly how that model is running and which particular models are present in OpenFOAM. So if you type LES and you're using any of the LES models, if you're typing RS and using any of the RS models, those equations are already present in OpenFOAM. Now, if you want to change any of them, if you want to introduce anything custom, you can make your own libraries as well. And you have the GitHub repositories also. They also have a few pre-built custom libraries you can compile. They usually give the instruction sheets of how to compile a library as well. So you can have a look at that as well if you're trying to do something custom or you're wondering how exactly is is the turbulence modeling linked with OpenFOAM. So you can check all of these backend files because everything is there within this, and everything is in C, C++. So if you know C, C++, it is really simple. And the equations also are not entered in a very difficult way. You can always open that. So if even if you're looking at it at the first time, you will know, if you have seen the equation, you will know exactly what is happening. Okay. So Mr. Mahesh, you wanted a step-by-step demonstration on command how to download a case file on Windows, copy it into WSL and run it with OpenFOAM 9. I'm facing issues, would appreciate detailed instructions. Okay, so Mr. Mahesh, by download exactly, do you mean from the portal itself? Okay, okay, so I'll show you. Okay, so see, if you have the portal, like say I were to download this particular research migration, you download it and it will show up in your downloads folder, right? Yeah, this one will download fast. Yeah. So once it is downloaded, you can go to your downloads folder. Okay. So it'll be something like this, right? So you can either copy paste the whole thing or you can extract it and then copy. Now for this demonstration, I'll just copy it directly. So you copy and you go to OpenFOAM 9 or 2412 or whichever version it is on. So say I were to go to the run directory for this one. So this is my run directory for 2412 and I'll just paste it here. Okay. So once it is pasted, I can just extract it. Okay. Extract. I'll use WinRAR to extract. So once it is extracted, just refresh it. Then now this comparison of viscous this. Again, inside this, you will have another file because the files are uploaded separately and the abstract is uploaded separately. So once you're done with extracting it, okay, this one did not extract it properly. Yeah. So you get the idea, right? So you have to just extract this particular file and then you're good to go. You can just type OF9, you can just right click and open in terminal, or you can manually open your terminal and type run and go to this particular run directory. And then do if there's an all run script, you can just do all run or all clean. So based on that, you can see which one is available. Okay. Simulation on. Okay. Yeah, there were a few people who had emailed us also regarding this case because we had demonstrated it like in a very short manner for the awareness session that we had last time. So in that, many people had joined and they had said that we will try this case, and they tried it and they were facing these issues. So we thought of taking up this case and just trying to resolve all those issues that they were facing before, because many people said that they had kept their systems on for like a day or something and still the results were not available. So at first we thought that it was just some commands that it was wrong or something, but then we tried to resolve that using this. We found out that the all run itself was faulty, so those commands you can just bypass them and it runs fine then. Okay, so if there is no more questions, we can break for lunch.